Let's start with a thought experiment. Imagine you could build a magic coffee filter, a filter that could reach into the liquid and selectively pull out the bitterness, while leaving every other nuance of flavor exactly as it was. Let's say the profiles are acidity, sweetness, and bitterness. In our minds, we imagine this as a simple subtraction. We just take the bitterness out and everything else stays the same. But in the real world, nature doesn't work that way. As soon as you remove the bitterness, you find you've also changed when the remaining flavors hit your tongue. Suddenly, the acidity arrives too early or the sweetness lingers too long. By trying to change the what, you've accidentally messed with the when. This is the central mystery. If you change the makeup of a signal, you inevitably change its timing. That idea, that frequency and time are locked in a permanent, unbreaking embrace, is the heart of a fundamental principle in physics, the Kramers-Kronig relations. When engineers design filters in audio, radio, or optics, we usually think about frequency response. Basically, how much we boost or reduce each frequency. Now, a frequency response, h omega, is actually made of two parts. The first part, h omega, is the magnitude. It controls how loud or strong each frequency is. The second part, phi omega, is the phase. It controls the timing, exactly when those frequencies arrive. In most software, you see these two plotted as separate graphs, amplitude in one and phase in the other. This creates a subtle illusion, the feeling you can just adjust the volume of a frequency without ever messing with its timing. But here's the catch. In any real physical system, you can't change one without changing the other. Tweak the amplitude and the phase shifts along with it. That's why some filters that look perfectly flat still make the audio sound smeared or ringy. The timing is off, they are locked together. So, where does this constraint come from? Why are frequency and time so deeply entangled? In mathematical terms, we describe a system's response with an impulse response, h of t. For a causal system, this function must satisfy a simple constraint, h of t equal to 0 for all t less than 0. All this is to say, before time 0, before the input arrives, there can be no output, the response is 0. When we take the Fourier transform of a causal system, we get a complex function, h omega. Usually, we think of the real and imaginary parts as two independent variables, like two separate knobs you can turn however you like. But because our system is causal, those knobs are actually locked together by a hidden gear. Time forces a relationship in frequency. The fact that cause precedes effect forbids them from being separate. Now let's look more carefully at what's actually inside a frequency response. Any h omega can be split into two components, h1 omega and h2 omega. Think of it geometrically. A purely real response, just h1, means the output is perfectly in phase with the input, no delay. A purely imaginary response, just h2, means everything is rotated exactly 90 degrees out of phase. But because h of t is real and causal, h omega must satisfy specific symmetries. The real part must be even, and the imaginary part must be odd. If you know the real part at positive frequencies, you automatically know it at negative frequencies. It's mirrored. And if you know the imaginary part on one side, you know the other. It's flipped. This is the fingerprint of reality itself. These symmetries are the signature that a system exists in our universe, where cause precedes effect, and through Kramers-Kronig, these symmetries become a constraint that binds amplitude and phase together. How exactly are they connected? The Kramers-Kronig relations make this precise. They say each part of h omega can be computed as an integral over the other part, across all frequencies. The real part, at frequency omega, is determined by integrating the imaginary part over every other frequency. That symbol, the Cauchy principal value, is a careful mathematical way of working around this singularity, where the denominator becomes 0. If you give me the real part everywhere, I can reconstruct the imaginary part. You don't get to choose both. It's a consequence of analyticity. Because h of t is causal, h omega is analytic in the upper half of the complex plane. And for analytic functions, knowing their behavior along with the real axis determines their behavior everywhere. What does this mean in the real world? In audio, it's why boosting the bass smears the timing of a kick drum. Change the amplitude, and time must follow. In optics, it's why absorption and refraction are linked. If a material absorbs light at one color, It must change the speed of light for the colors nearby. You don't measure the refractive index, you derive it from the absorption. In radio, it's why brick wall filters distort high-speed data. A sharp cutoff in frequency forces violent swings in phase. Real-world design is always a compromise. You can have a sharp transition, or you can have a perfect timing. You can't have both. So the next time someone talks about perfect control, remember, if your system respects causality, its amplitude and timing are inseparable. This isn't an engineering limitation, this is a law. A consequence of causality expressed through the deep structures of complex analysis. Physics becomes geometry, and geometry becomes the constraint that governs everything from the sound in your ears to the light in your eyes.